Hi there, I have a nice problem for you, which was proposed by one of my friends other day when we were playing pool. And I closed my eyes for a second after the question and I solved it in seconds. No, just kidding. It took a while to solve it. But I think it was a cool problem and I would like to share you the solution. Also, this sequence may look familiar to you if you're a strict subscriber. I don't know if that exists. I made another video about this sequence, and in that video I showed that only the first term in the sequence is a perfect square. If you would like to see that video, you can go to this link. I will share it here. And now let's see this problem. So the task is to find an infinite subsequence of this sequence such that all of the terms will be relatively prime. So first of all, what is relatively prime? It means they don't have a common divisor other than 1, okay? And what is subsequence? It means you will just pick some terms of this sequence, okay? We will just pick, like, for example, we will pick 11, 111, and then I don't know, the one which has 7 digits, and but this has to be infinite. Well, if it's not infinite, of course it's not interesting. Okay, so let's see. First of all, well, also in that video I generalized the term. So if we say an is the general term, it will be like 10 to the n minus 1 over 9. Well, this is easy. You can either do it with geometric series or just imagine it like it's 99999 over 9, and this is 99999. Okay, so this thing has n digits. Okay, this is 1 1 up 1, and this has n digits. And well, it's a bit hard to work with this thing, so instead I will try to work with 10 to the n minus 1. So how can I do that? Well, the way I can do this is that so for example, if a prime number q divides let's say 10 to the n minus 1, okay, 10 to the n minus 1, which is 10 to the n minus 1 over 9 times 9. So I know that if q divides ab for any prime q, then q divides a or q divides b. So this means that if q divides this multiplication, q will divide this or this. And if I say that q doesn't divide this, it will be equivalent to saying that q will divide 10 to the n minus 1 over 9, okay? So if I add the condition, q doesn't divide 9, which is only prime that divides 9 is 3. If q is not equal to 3, and if I say q divides 10 to the n minus 1, then I'm gonna have q will divide an, which is 10 to the n minus 1 over 9. Okay, so this is the first step. Instead of like dealing with this thing, I will just deal with this thing, okay? And now and I will just deal with the 3 case. In the end, it's very easy case, okay? So again, and let's try to formulate what is relatively prime. So if I have a number, if I have two numbers relatively prime, this means that, so for example, if a and b is relatively prime, then this would mean that their GCD is 1, which would mean that only, for example, some prime numbers would divide a, some prime numbers would divide b, but they won't be common. So this means that any prime number q that divides a and b, this is a contradiction. For any prime number q, it can't divide both a and b. For example, if I assume this, then I would need to get a contradiction so that I would see that this is wrong, so their GCD is 1. If I assume that q divides a and b and get a contradiction, this means that a and b is relatively prime, which means their GCD is 1. Okay, so this is the big idea. And now let's see. Let's get to the question. Okay, so we're gonna explore some facts, and we will just get there. Okay, so the first one, let's just explore some properties of this sequence. So again, so like I said, I will just pick two numbers, okay? So I will just say that, so for example, q divides 10 to the p minus 1. And let's also say q divides 10 to the r minus 1. So I'm just picking two numbers from this sequence like a and b, and I will try to get a contradiction, okay? So I say let q divides this and this, or assume that q divides this and this. And is there a contradiction? Contradiction. Okay, so the first property about this sequence is that, so, well, I know that 10 to the, let's say 10 to the x, for example, if 10 to the q divides 10 to the p minus 1, what would I get? This would mean that 10 to the p minus 1 is congruent to 0 mod p. Well, I can just add 1 to both sides. So I will see that 10 to the p will be 1. And now I can just take any power of all sides. And 1 to the a will still be a. Sorry, it will still be 1. And so this means that if q divides 10 to the p minus 1, then 10 to the p to the a will also be 1. So this means that p will also divide 10 to the pa minus 1. Q will divide 10 to the pa minus 1, which means for any multiple of this power, q will also divide that. Okay, so this is the first property. And second can be the addition one. So for example, I can just imagine q divides 10 to the p minus 1, and it also divides 10 to the r minus 1. Well, then I can just multiply all sides, okay? So q squared will divide what? Just this multiplication, okay? 10 to the p plus r. And then I'm gonna have plus 1 and minus this sum of these two, minus 10 to the p plus 10 to the r. And well, I could also just add them, and I would see that q would divide 10 to the p plus 10 to the r minus 2. If I add them, q also divides that. These are the basic properties of division, divisibility. So I know that, well, it's also true for negative of it, doesn't matter. So I can just say like this, plus 2. So I can just try to get the same thing on this side. Well, if I make this 1 into minus 1 and add 2, well, this thing will be this one. So q divides this thing. And if q divides, also, since q is prime, q divides q squared. This is an obvious fact. So q divides this whole thing, and it also divides this piece. So q has to also divide this piece. So this means that if q divides 10 to the p minus 1, 10 to the r minus 1, q will also divide 10 to the p plus r minus 1. Okay, so we can just add the powers. And at the first step, we learned that we can just multiply the powers by something. So I can just also combine these two and make it like a linear. So from this 1 and 2, I can say that q divides 10 to the p minus 1, 10 to the r minus 1. Then q would divide 10 to the ap plus bq minus 1. Because it would, of course, divide 10 to the ap. Also, wait, this is r. And it would, since it divides 10 to the r minus 1, it would divide 10 to the b r. And I know that if it divides two numbers, then I can just add them. So I could just add the powers, and it would also divide this one. Okay, so this is very important. I actually tried to go from this way, but I actually needed to combine it with something else. Okay, so now let's explore another property, which I explored before, but I couldn't combine them. It requires some time to think about it. Anyways, and the last property I can think about is that, so I can just try to use the fact that q is a prime number. Okay, so I know that q divides 10 to the p minus 1 and 10 to the r minus 1. Well, then I can, so there is a number, well, I used a and b, let's say c, that, so c times q will be equal to 10 to the p minus 1. There will be a c number, c integer, and also there will be an integer. Well, this one I can say d times q will be equal to 10 to the r minus 1. This is because q divides 10 to the p minus 1 and q divides 10 to the r minus 1. And now I can just subtract these two, and I'm gonna get at q parenthesis c minus d will be equal to, also I think till here I didn't say if p or q is bigger, but of course one of them is bigger. And actually in the end, I mean, if they're same, it doesn't make sense. I mean, it's just not useful. We just need two different numbers. So let's also assume p is greater than r. I mean, it can be other way too, but without loss of generality. Let's say p is greater than r. Later I will also say these are prime numbers. It's why I'm using p and r, because I just guessed that the answer may be only prime numbers. But till here we didn't use anything about p and r being prime numbers. We still didn't assume p and r is prime number. Okay, so you can imagine it like not being prime numbers, but one of them is just bigger than other one. Okay. So now, well, I will have 10 to the p minus 10 to the r. I said 10 to the r is less than p, so I can just take it into 10 to the r parenthesis. And it will be 10 to the p minus r minus 1 when I subtract them. Okay, good. So this would mean that I can just divide both sides by q, which means that q would divide 10 to the r times 10 to the p minus r minus 1. Okay, cool. What does that mean? So like I said in the beginning, if q divides a multiplication, q would divide at least one of them. Okay, so q would divide 10 to the r, or q would divide 10 to the p minus r minus 1. Okay, still no contradiction. It will take a while. So can this be the fact? Well, this is a bit weird because I know that q divides 10 to the r minus 1. So because I know 10 to the r minus 1, I can just subtract these two, and I would get that q would divide, well, their subtraction is just 1. So q would divide 1. Well, no prime number can divide 1. So this is a contradiction. Okay, so q cannot divide 10 to the r. So from here, I have to admit that q would divide 10 to the p minus r minus 1. Okay, so what I said on this third property is that if p is bigger than r and q divides 10 to the p minus 1 and 10 to the r minus 1, q would also divide their subtraction of the powers. Okay, 10 to the p minus r, yeah, minus 1. Okay, perfect. We are done. After this point, we will just try to combine them. So actually, after this step, I just thought that, well, if I pick p and r relatively prime, I can achieve to get ap plus br being equal to 1 because of the Bezos theorem, which says if, for example, p and r is equal to d, then there exist constants x and y such that these are both integers x and y, such that xp plus yr is equal to d. And if their GCD is 1, then I can just make this thing equal to 1, and then I would see that this is q would just divide 10 to the 1 minus 1, which is 9. But in the beginning I said q is not 3, so it won't divide 9. So I would get a contradiction. It would be nice, but it's not that simple because I can't choose random a and b, because I know that from this property, this a, so this power a has to be positive. I can just take negative powers randomly and hope that this will be true, because, so for example, if q divides 10 to the 2 minus 1, well, I can't say q will also divide 10 to the minus 2 minus 1, because this is not even an integer. And 10 to the minus 2 may not be defined. So this second property is actually true for a and b is greater or equal than 0. But I know that P and R, well, they're just natural numbers, at least, if not prime, and they are both positive. So A and B cannot be positive at the same time, because then how will I get to 1? So one of this would be negative. But I want to achieve this thing. So here I made some deep thought, like, can I uh, increase this A bit and decrease this B a bit so that they are both positive, or I mean, just some extra details, but it doesn't work and it's not useful. So there's a simpler way. I can just combine second property with third, which says, so I know that Q, if Q divides 10 to the P, it will divide 10 to the AP. And it also divides 10 to the BQ. Well, now combining this with the third property, that I can say if AP is bigger than BQ, then I know that it would divide their subtraction. So Q would divide 10 to the AP minus BQ. Well, this is the key point that I missed before. -1. Also, there are -1s here. It doesn't matter. Q would divide then A to the AP, 10 to the AP minus BQ, -1. Can I achieve this thing? Of course. I mean, P is greater than Q, and I can just pick some A and B, and of course AP will be bigger than BQ. And now the question is, can I get AP minus BQ? AP minus BQ being equal to 1. Well, first of all, if I can find that it's equal to 1, this would mean that it's positive. So this is my condition for the third property to hold. And well, I can of course achieve this, because now if I think, I know that again, because of the Bezos theorem, this thing has a solution, since also, wait, this is oops, this is R again, BR. Did I say Q here? AP bigger than BR. These are R. Q is what divides it. Okay. Can I achieve this thing? Yeah, because I'm going to assume that P and R is relatively prime. If their GCD is 1, then this thing would have always a solution. Well, it actually has infinitely many solutions. You can look up linear Diophantine equations. So basically, if there is a solution, A and B, okay, and there is a solution because of the Bezos theorem, also A plus, for example, I can just pick any constant multiplied by K, KR, A plus KR, P minus, and for this constant I will decrease this one by P. Wait, since they are both minus, I will actually increase it. It will be B plus KP. So I'm just, on each step I can increase this one by P and this one by R, and this will still be a solution, because if you think I have AP minus, wait, this is R, minus BR, which is equal to 1, and KRPs will just cancel, and this will still be true. So with this way I can show that there are infinitely many solutions. And well, so from this, if one of these A and B is negative, well, I can just increase them. Yeah, I can just pick K is positive, okay? And with this way, I could assure that A and B can be positive, such that this holds. And I also know that AP is bigger than BR. So there is always constants. There are always constant A and B, integer, but also positive number, such that AP minus BR is equal to 1. Okay, this is the key point. So what did I say? Well, so I said that if Q divides 10 to the P, it divides a multiple of it. 10 to the R, it divides a multiple of it. And then, so these are for any multiples A and B. And if I pick this specific A and B, Q will divide 10 to the AP minus BR minus 1. And I found that for some A and B, this can be equal to 1. So this will be just 10 minus 1. which is 9. And if q divides 9, q is equal to 3. Well, in the beginning I said let's solve for q is not equal to 3. I found that q is equal to 3. This may not be a direct in contradiction, because, well, then, so okay, q can't be 3, but maybe it can be 3. Now, and let's see if q is equal to 3. So from here, I see that q has to be 3 to satisfy these properties. Okay, so q cannot be something that is not equal to 3. Can I say it like this? Anyway, it's just saying the same thing with this one. Okay, okay. So I found that q has to be 3 to satisfy these ones. And now let's see why it can't be 3. Well, this is very easy. I know that. So what I want to show is 3 divides 1, 1, 1 something. Okay, and well, I don't want a q to divide this, and I know that the divisibility property with 3 is just saying that you just add the number, you just add all of the digits. If it's multiple of 3, then it will divide 3, and it will divide it if and only if the multiple addition of all of these digits is multiple of 3. So, well, if this thing has n digits, the sum of digits is n, and well, this will 3 will divide this if and only if wait, this is a bit bad writing. Let's say this will divide, this sum is n, if and only if n is equal to 3k. If n is like multiple of 3, it will divide. But since I want them to be relatively prime, I can just pick all of the numbers that are relatively prime with it, p and r, such that they are not multiple of 3. And if I say that, well, then 3 won't divide any of these numbers. Also, well, I can actually also include 3 for only one of them, because, well, I will of course not, so for example, I can include 1, 1, 1, but I will not include 1, 1, 1, 1, 1, 1, 1, 1. I don't know how many ones I said, but 6 of them, because I know that if q divides this, q also divides this, because 3 divides both of them. But I'm saying that of course I will not take, if I take the third power 3n case, I will of course not take 6n case. I want 3 and 6 to be relatively prime, but here it's not. So it's why the simplest way is to just pick all of the numbers that is in the form of 10 to the p minus 1 over 9. So if I have p digits 1, 1 up to here, if I have p digits where p is a prime, then I'm guaranteeing that 3 will not divide it, because sum of digits will not be 3k. Okay, except for p is equal to 3, but it can be 3 because the primes go like 3, 2, 3, 5, 7, etc. And only 3 will divide this one, but none of the other ones. Okay, and I also know that q can't be different than q can't be different than 3, because I said that if it is different than 3, well, then I found a contradiction here. Well, q has to be divide 9. Okay, and that's the end of it. Okay, yeah, I hope it was clear.